Okay, in this video, we're going to show you how to do the stock prediction used ARIMA. So this is actually referring a blog posts that is available right here. I simplified it a little bit, but most of the code and the example is actually using that blog. So this example is purely to show how to use the model to predict a stock. The model is called ARIMA. It's a statistic model, but this is just purely for coding. It's not for investment or trading strategies suggestions. I have to disclose that I am not very good at trading at all. So don't use it seriously. Just think it about just try to give you some ideas about to use the code to help you to find some models. And we do have several finance firms in town, so hopefully this will prepare you for those kind of jobs. And first of all, what is ARIMA? ARIMA is called autoregression model. AR is for autoregression. MA is actually moving average. So the whole thing is called the autoregression integrated moving average model. So all of them are actually statistic models, and all of them can do certain prediction. However, in this video, we're going to introduce the ARIMA model, and this actually has a very has a condition. If you want to use it, the condition has to match, has to meet. So the condition is the data must be stationary. What does that stationary mean? It means the probability density function does not change to according to the time. So if the time changes, the density function should stay as is. It does not change. So when we do the prediction, the condition probability will actually make the meaningful prediction based on the previous probability. So if the base probability is changing with the time, so there's no point you can predict the future value. So it has to be that way. However, stationary is kind of very, very hard to meet the condition. Barely there are some data are actually stationary in time series. Most of time series data are actually changing the value according to the time. So but we do have a way to see if the data is kind of like semi stationary. So what we can do is we can actually take a difference of the value. That's called the first order difference. And if that is not enough, then we can take the difference of the difference. That will become our second order of difference. But most of the time, either the first order or second order of the difference will normally make the data kind of like semi stationary. As long as the data is semi-stationary, we still can use the model. So that's the good thing about the model. Some models requires the data has to be stationary, so you have to meet that condition, otherwise you cannot use the model. So in data sciences or data stat analysis, keep one thing in mind, even machine learning, or deep learning. So all of them follow the same philosophy. That is called garbage in, garbage out. So if you throw some data that is this garbage, then your results is meaningless. So you can't use it. So let's do the coding for here. And before we do that, keep in mind the ARIMA model is like a black box. It's like a black box, like a function call. You don't know what's the detail, what's the statistic model, what's the density function, what's the what's the all of those functions, what's the probability distribution, what's the hypothesis. You don't have to know because we're not majoring in statistics or math. What we can do is we're doing the coding. We know this black box, we throw some stationary data, it's going to give us the prediction. That's all you need to know. And then now let's do the coding. When we have the coding, we're going to break down to several steps, roughly about 6 steps. So step 1, you're going to retrieve the data, prepare your data, clean your data, and then you're going to start to do some test of stationary. Once the stationary test is passed, then you can actually doing the actual training, and then you can do the modeling. So let's first get the data. To get data, I would suggest you install the Y-Finance, which is a model that can allow you to download the data from Yahoo. The Y stands for Yahoo Finance, right? Which is a great contribution to the community. Yahoo, even the website itself is kind of like going down, but the Yahoo Finance is one of the greatest utilities that can be used. So you install this utility, and then you can actually import the pandas and the Yahoo Finance, and then we have that. Then we're going to first get the YF ticker. You get spider. SPY is it's a index of SP and 500, and so that will give you the tick, and then you get the tick information about the stock information. You actually get the history data, and you save the history data. So in the future you can directly use it. And here you can actually read it directly from history data instead of every time you go download and save it and then read. So this one, you save it on your own computer, then you can read it and download it and directly use it. So we actually prepare the date. The spider date has actually a column, because the spider was a time series, so the dates actually was used as index. But here we want to turn it into a column, so the index becomes 0, 1, 2, 3, 4. And then here I printed the header part of the data. So let you take a look how this data look like. So the dates now becomes a index, and becomes a column, and then you have open, high, low, and close data, and then you have volume, you have dividend, stock split. So those are the basic data, right? And then we can use our split data. We can split our data since we're only interested about the closed data. Most of the models, or most of the coding to the stock prices are using closing data. So we can actually have the NumPy, have the pandas, and then have the matplotlib, and then we can get the closing data. So here is going to give you what's the split data, and then what's the index, and then you get the training data, and then you're going to get the test data. So all of them are doing the same thing. Basically, it's just the slice part of the whole set of data. Like one portion is the training, the other portion is the test. And again, those cutting off dates are arbitrary. You can set up your own dates, so it can use it. But the general rule of thumb is you use 80% of training data. So the training data, you are going to use 80% of the data, and then test data, use 20 or less of the test data. So you can evaluate how well this model is performing. So we basically prepare all the data. Now we're going to test if the data is stationary. So to do that, we basically are going to use one of the model. It's called the augmented Dickey-Fuller test. It's a statistic test family or family for the testing. So to test if this is a stationary. To draw a conclusion, once you run this model, you get some results. How do you know the data is actually stationary? You're going to check two values. One is the p-value, the other one is the test value. The p-value has to be less than 5%, and the test value has to be less than all critical values, 1%, 5%, and 10%. Both conditions must be met before you actually can conclude that the data is stationary. So let's first load the model, and then here we write a function. This function is kind of standard. So all you need to do is first you get the rolling mean average or mean, and then you get the rolling standard deviation, and then you can plot all the rolling statistics. What's the original, what's the mean, what's the statistics. Then you can plot, and you can show the results. You can show the picture, and then you actually get all those test and outputs values, and also the p-values. So here, that's the definition of the function. Then we call the function, and the series number is actually the original, the closing data right here. It's the closing data of every day. So that's actually a series data. So now we plot this, and we run this, and in the function it's plot the results right here, and we get the results as well. And you will notice that the results, let's look at the last part. So you will notice that p-value is 1. It's definitely not less than 5%, which is 0.005. And I'm sorry, it's 0.05. And then that's p-value is 1%. It's not less than 100%. P-value is 100%. It's not less than 5%. And test value is 2.8. And all the critical values, 1% is -3. They're not less than. So both the conditions are not met. So which is not good. Then we're going to do a difference of the value. So basically means that we're going to take the subtraction of today's value close price to yesterday's close price. So that's called the first order of difference. You will notice that in here, difference _1. There are actually, if this is difference of the price is not stationary, then you can do a secondary difference of the price. That's second order of difference. And then you get the results. You get the difference value, so you prepare it. And then you are going to drop all the NA. This step is important because all the values are, if they're null, that means they're not valid data. You have to clean it up. Like I mentioned earlier, always keep in mind garbage in, garbage out. So make sure you drop all the null values. And then you are going to do the test the dictionary, test the stationary. So you use the new difference value of the closing data, closing prices, and all of a sudden you see this figure, which is a good figure because that's look like a white noise, right? Like a noise. That means they are not related to the time. So, and let's take results of the p-value. P-value is 0. It's less than 5%. Test value now is a -20. It's less than 1%. And if you look at the very bottom, that's actually have all of it. So the test value is -20, is less than -3, less than -2, less than -2. So we met both the condition. So we can draw a conclusion that the price of spider is actually semi-stationary. So once we have that, then we are going to further check if they have the autocorrelation and partial autocorrelation This is again validate that this is a stationary. Auto correlation is actually between the two next values, like t and t minus 1, while partial autocorrelation is between any two values. So you take the you want to see how they are related to each other, and by taking the laps, so-called lags, that will basically showing you if you are moving the whole data as a window, like T1, T2, if their lags is just 1 day. If it's 0 day, it's itself, 1 day is right here, 2 days right here. So you do this results, you will find the results are plotted right here. How do you read the results? You basically want to see the value will quickly or sharply drop to 0, or somewhere close to 0. So that means it's good data. Same thing here. For partial autocorrelation is sharply dropped to 0. That means it's good because they converge quickly, right? Converge quickly. So, and so you can now next step is we're gonna train our data. The training can take a very long time, and depends on your computing and all the memory resources. My computer is kind of slow. It takes quite a half an hour maybe to train this data. So you first import the model that we're interested, ARIMA model, and then you're going to directly make a spider ARIMA model. You get the trained data. Training data, remember, was from the whole set of data. We slice 80% or more data as our training data. Then we fit into the model. Here's the fit. The fit actually means it's training. So this is the training. So we have the trained data. Then we're going to print out the trained summary. In this, when I do this lecture, I don't have the the result is actually right here now. So it's actually trained the results. You will find it's doing pretty well. Like standard error is relatively low. And then you can use that data actually doing the forecasting. So to do the forecasting or prediction is you are going to get the history, and then you get the model prediction as a list, and then you count the number of tests data points, and then you have a for loop. You for each of those test point, you do the training. You do the model and then do the training, and then you get the forecast, the prediction. You save the prediction eventually into the model prediction list, and then you get the true value, and then you get the prediction value and the true value. So later we can plot them, and you can see how much the difference. And eventually we're going to have all the trained data, a trained model actually saved in here. So that's actually our trained results. So this again takes forever to do it, but once you have it, you're going to actually see the results. And here I actually have another trained data I can show you. This is actually the trained data. So you see, once the training is done, you see the standard arrows. The mean standard arrows will be somewhere close here. At the beginning is probably big, and then you see it becomes smaller and smaller. And then, so sometimes it's higher, sometimes slower, right? And then you can actually load the model from the file to load it. And here you can actually run that model, and then you can do the test data. You can see what's the average error. So the average error is about $23. The price is about $400. So you will see it's relative, it's about 5% errors. So it's not, I think it's acceptable. But again, I am horrible trader. I'm not good at that. So you probably can do your own judgment. But here is purely from the math and coding standpoint. I would say it's pretty good. It's close, right? So you can plot the results of the prediction value, which is the blue one. The actual value is actually the red ones. So you see it's pretty much close. It's not too bad. And eventually you can see you can do a prediction like what's tomorrow's price. It's going to give you what's next day's price. And you can check. Okay, that's all I want to introduce in this video. If you have any question, please let me know. Thank you.